So last time we just started the last section of this unit about functions. We talk about the functions on unit sets. There are several interesting facts about functions on finite sets. Either the domain or codomain is finite or both, especially with respect to the injectivity and surjectivity. There's some interesting results. And then we discussed partitions and the pasting functions. These are actually piecewise functions we learned before. In some cases, you may have a large set in domain or a complicated function in a domain that you need to partition the domain as a set into subsets, and then you define a individual function on each subset of the domain. And correspondingly, you get a different code domain for each of those functions defined in the subsets of the domain, and then you can combine all the subsets in the domain and combine all the codomains from those functions and define a large domain, a large codomain, and that will make a function from the large domain to large codomain if you just combine all of those functions together. So that's how it works for piecewise defined functions. But the one thing to keep in mind is when you talk about the partition, by definition, it cannot be empty. The subsets of a partition of any set cannot be empty. There cannot be any intersection between those subsets, and the union of all the subsets should be equal to the universal set, or to the whole set. Okay, so yes, and on Monday we just talked about one example about about these partitions, and this process we call it the pasting functions. It's just like pasting different pieces together to make one function from a bunch of functions on different domains and the codomains. So in this example, we have set A with 10 numbers, and we can partition it into 3 subsets, P1, P2, P3, and then we have another set B with 5 numbers, and we also can partition set B into 3 subsets, Q1, Q2, Q3, and then we just defined 3 functions, F1, F2, F3, from P1 to Q1, P2 to Q2, and P3 to Q3, respectively. And then you just put all the 3 functions together, then you get the piecewise defined functions like this. Okay, it's very helpful if you draw the diagram of the sets with specific elements in each set, A and B. Okay, so the left hand side is set A with 10 numbers, and we split it into 3 pieces, or partition into 3 subsets. On the right hand side, we have the set B also partitioned into three subsets as defined in the problem or in the example, and then F1 is just from P1 to Q1, defined like this. You know, map 1 to 1, 2 to 2, 3 to 3. So that's Fy(x) equal to x. And then you map all the numbers in P2 in one number, which is Q2, and you map all three numbers in P3 and to one number, which is 5, or Q3. Okay, so these are three separate functions, but we can, paste them together, paste the domains together and paste the codomains together, then we get the one function, right? It makes one function because all of three individual functions, component functions, if you will, they're all functions. So each of the element in the whole domain just maps exactly one element in the whole codomain. All right, so it's nothing really hard to understand it. Well, there are some interesting properties about partitions and pasting functions also. That's called the pasting together theorem. And again, we talk about the injective and surjective. Essentially, this theorem says if each of these fi is injected, then the whole the pasting function f is also injective, and if each of fi is surjective, then f is surjective, and if each of fi is bijective, then f is bijective also. So that's pretty natural, right? So if you get all of those component functions have the same property, then it should keep in the pasting function. Okay. So we can easily prove this theorem. For example, part A. So we just assume each of these fi is injected, then we need to show f is injected. So so the typical way to show injective function is to to just assume fa1 equals fa2, where a1, a2 are from the domain, and then you should come to a conclusion that a1 equals a2, right? And that proves the injectivity. Okay, so let's just a1, a2 are two different elements in the domain A, the whole domain, the large domain. So because this large domain A is pasted from the subsets P1, P2, P3, or Pi, or whatever, then any element in the domain, the large domain, must be from a specific subset of it, or one of the PIs, and only one of the PIs, because those PIs are disjoint. Remember, partition means the subsets are disjoint. So then we got the A1 from some PI, subset A, and A2 from another subset PJ. So, well, because we have assumed that fa1 equals fa2, and obviously from the pasted function, this fai is just the equals f of I A1, which is QI, which is in QI. We just the function fi is from pi to qi. So if a1 is from pi, then f of a1 will be, of course, fi of a1, and it will be in qi. And similarly, f of a2 is just fj of a2, and that's in qj, because fj is from pj to qj. Okay, so because fa1 equals fa2 by assumption, we start from this. So then they have the same qi and qj have a common element. fa1 is one of the elements in qi, and fa2 is one element in qj, and these two elements are the same. So that means qi and qj intersection is not empty, because fa1 and fa2, obviously they're the same. Okay, but again, the q's are partition of p, so they cannot, if the two subsets qi qj of b are disjoint, then they cannot have a intersection. But when they have intersection, then they must be the same. They must be equal. Okay. So then qi is just the qj. Okay. So then fi is just the fj. Okay. So fi a1, which is fa1, and fj a2, which is fa2, is actually fi a2. So this a1 a2, they are defined, they are evaluated in the same component function fi. But because each of fi is injective, if fi a1 is equal to fi a2, then a1 has to be the same as a2. So if you go back to the assumption, for the basic function, we just assume that fa1 equals fa2, and we come to the conclusion that a1 equals a2. So that proves that the basic function f is injective, right? So that's the first part. The second part says, if fi is surjective, then f is surjective. This is also easy to show. The basic function is surjective. So let's just say some element b in b in the codomain b. Then we have to show there's a pre-image of it from the set A, right? So we know the set B, the codomain, also comes from the union of the disjoint partitions of QS. So B must be from one of those QS. Okay. And the function fi is defined from pi to qi. So because fi is surjective, okay, each fi is surjective, that's the precondition. So then there must be some element in pi such that the f of I of that element A equals B, right? We call this element A. So then we're done, because fa is just the fa because A is in pi. So that's how it's defined, and that's equal to B. So we have shown that any element in the codomain B has pre-image A in pi, which is also in A. So that proves the surjective of the function f. Now, part 3, comes directly from 1 to 2, because each wave is bijective, then it is both injective and surjective. So from 1, then we know F is injective, and from 2, we know F is surjective, so that F is bijective. All right. Any questions about theorem? If not, let's go to another example. So let's just define a function f. Well, actually, let's just start from the two component functions, f1, f2. So let's just define the function from n to z. Okay, the paste function, but we're going to partition the domain n into even and odd numbers, p1, p2. So p1 is a set of even natural numbers, p2 is a set of odd natural numbers. And then we also partition z into q1 and q2, where q1 is the set of positive integers and q2 is a set of non-positive integers, including 0. Okay, so 0 and negative numbers. And then we just define the one function from P1 to Q1, another function from P2 to Q2. And we call them F1, F2. F1 is defined as NO2. Okay, so remember F1 is from P1 to Q1. So P1 is set of even integers. So N is an even integer here. So if you divide by 2, you get another natural number, right? So that makes sense. Or an integer, I mean, positive integer actually. Okay. And F2 from P2 to Q2. So that's from the odd natural numbers to non-positive integers. Okay. So what is it defined? So it's defined as F2 of n equals negative n minus 1 over 2. Okay, so n is odd natural numbers starting from 1. Okay, so the smallest number n is 1. So when n is 1, we get 1. 1 minus 1 equal to 0. So we get 0. The function value is 0. And when a is greater than 1, then n minus 1 is positive, a positive even integer, right? Because n is odd. So then you can divide by 2 to get the integer, but then there's a negative sign in front, so that makes a negative integer. So this F2 is indeed from P2 to Q2, from odd natural numbers to non-positive integers, right? So well, this P1, P2 is a partition of n. The union of the two is the set of natural numbers. They are not empty, and they don't have any intersection. Intersection. The intersection is empty. In other words, same for Q1 and Q2. Q1 and Q2 they are not empty. The set, the union of Q1 and Q2. Q1 is positive integers. Q2 is not positive integers. So that makes integers if you union them, and obviously the intersection of them is also empty. So then everything just satisfies the condition for the pasting function, so we can paste them together to get one function which is defined piecewise from n to z by this two formulas from those two component functions. So f1 equals the number 2 if n is even, and f1 equals negative of minus 1 over 2 when n is odd. Well, you can easily check that f1 and 2 are bijections. That's pretty easy to show, right? So for example, first M1 F1 is P1 to Q1 is 1 by 1 because you know if you change the number and the even natural numbers, you divide 2, you get a different positive integer, right? So it's 1 to 1, and it is also on 2 because the even natural numbers for starting with 2 and go 4, 6, and so on. If you divide by 2, you get a 1, 2, 3, 4. So that makes a whole natural numbers. I mean, whole positive integers. I'm sorry, right? Similarly, so is F1 is 1 to 1 onto, so it is bijection similar for P2. I mean F2. It is 1 to 1 because if you change the odd number n minus 1 will be different, and you divide by 2, you get also different. I put negative number, that's also different. So it is 1 to 1. Also, it covers the whole non-positive integers. As I said, when n equals 1, you get 0, so that takes care of 0. And then if you pick up the other odd numbers, 3, then you get -1. If you pick 5, then you get the 5 minus 1 equal to 4. 4 over 2 is 2, so -2, and so on. So that covers all the negative integers. So it covers this this function. Actually, the range of this function f2 actually covers the whole set of non-positive integers. So it is on 2 also, so it is bijection. So from the theorem on the previous page, if we have one f2 are bijection, then f is bijection also. So this function is actually a bijection also, although it is piecewise defined. It looks weird, but it's actually a bijection. Any questions? So everything just become pretty interesting, but we just go to more in depth about different types of functions.
Okay.
And so that's the second topic for this section. And the next thing is called the restrictions of functions. That's also a very simple concept. So suppose we have function f defined from set A to set B, and consider a subset of the domain A, we call it S. Then sometimes we may want just to check the product of the function f confined from S to B. All right. So then we have this restrictions of functions. Okay. So let A, B be sets, and then let f from A to B be a function. If A is a subset of A, okay, it's contained in A, we can define a new function f. Is still from is from S to B. Okay, so S is a subset of A. You just take part of the functions. If you consider the f as all the pairs, just take a part of it. And you just use a vertical line subscript s to mean this function is a restriction of the function f to s. Okay. And obviously the rule will be just the f of x, the same function we defined, we start, but x just confined in the subset of s instead of a. So we call this new function the restriction of f to s, and you read it as F restricted S. Okay, when you see this notation, you should know that's what it means. Okay, so how does it make sense? If you look at some example, you see why we need that. Okay, and it's actually very normal, very frequent to have this kind of functions. Suppose we start from a function from R to R, defined by fx equal x squared. So that's just a parabola, right? Oh, quadratic function, standard quadratic function. And we know this function is not one-to-one, not a bijection, or not injective actually, because of course f negative one equals f1 equal to 1. Okay, if the square negative 1 equal to 1. So it's not bijection, bijection, but if you just restrict the function from non-negative numbers in the domain, so let's just define a subset S or the set of non-negative real numbers, then the new function f restricted S from S to R is in fact injective and bijection. So this the rule is the same, but the domain changes. Okay, so we restrict a lot of inputs. So sometimes we do need this kind of technique. For example, then this function is a bijection. Now you can talk about the inverse functions and so on, right? Okay. Well, we know a function is just ordered pairs. Okay, so if the original function from A to B, the set as B contains all the ordered pairs, A and FA where A is in set A, then the function f restrict to S will be the ordered pairs of the same numbers for A in S, right? So, okay. So we just defined, the function restricted by the domain, but you can also do a similar thing for the codomain. All right. So the next definition is just a similar thing for the restriction of function to the codomain. So let the function f from A to B. So you can define a new function f hat from A to the image of f. Okay. So remember, the image of f is the range of the f. So that's a subset of the codomain. All right. So that's part of the codomain. And the rule is still the same. Just take the function value of the original function f at each of A in the set A. And we call this f hat the surjective reduction of f. Okay, so you see the difference is the codomain. Now this f hat is defined from A to the range of A. So it is onto now. So this changes the function to onto function. It may not be onto before. Okay. And that makes sense, and we do need that kind of things sometimes. So for example, let's just talk about the previous example before. The function we have is still the quadratic function f of x squared defined from R to R. And we know, this function is not only not one-to-one, but it's also not surjective. It's not onto. If you look at the codomain R, the negative numbers doesn't have pre-image under f from f. You cannot square real number to get a negative number. Okay, so but you can make this function onto or surjective by restricting the codomain. Okay. So first, you just find the range of the function or the image of the function. We know that's all non-negative numbers. Okay, so from 0 to infinity. Okay, the square of a real number is 0 positive numbers, right? So then, if you just define f hat from R to this set from 0 to infinity equal to 0, then it will be a surjective function. So that's the surjective reduction of f. So that's why we call it the surjective reduction of f, because it is surjective now. So the rule is still same, but the codomain changes. So it's a different function. All right. There's some results about this restrictions function. They're pretty obvious. Okay. The first term says, if we have function f from a to b, then the surjective reduction from a to image of f is surjective function, as we already talked about. Well, we can easily prove it. Okay. If you consider the function as all the pairs. So first, it's function because it includes all the pairs, part of all the pairs from f. So that makes it a function. One element. Each element in the domain has exactly one element paired with it in the second coordinate from the codomain, right? So that keeps the f hat as a function. And then we need to show it's a surjective function. So you just pick up any number b from the image of f or the codomain of the new function. By definition, the image of f, the set of image of f means the set of all the images of set A. So any element in this image must have a pre-image in set A. So there is some number element A in set A, so that fa such that fa equals b, right? So that's from the definition of the image. So then fa equals b. So so for any number b in the codomain, you can always find a pre-image for it. So that proves the function f hat is surjective. So this theorem essentially says a function f is surjective onto its image. So that's obvious from the wording even. All right. And the next theorem, well, actually, the next topic for this section, sorry, is for images and pre-images. I have talked about this quite a bit, but let's just define this thing precisely. So the A and B be sets, and the f a function defined from A to B, and let's say A is a subset of A, and then we can define the image of S under this function f, or the image of S to be all the values of the function when the argument comes from the subset S. So we just use this notation f of subset set S to mean the set of all the function values under this S. Okay. So obviously fs is a set, and it's a set subset of the codomain, obviously. So that's the image of S. Okay. So you can talk about the image of a subset of the domain. All right. So let's look at one example. Suppose we have two sets A and B. Both have 4 numbers. A has numbers 1, 2, 3, 4, and the B has other 4 numbers 5, 6, 7, 8, and this function is defined from A to B. Has 4 other pairs, just pair 1 with 6, 2 with 5, 3 with 8, and 4 with 7. So you can talk about the image of any subset of the domain A. So for example, the set of 1, 2 is a subset of domain A, then f of that subset of A will be 6 and 5, or 5, 6, the set of 5, 6, right? And similarly, f of the set of 1, 3, another subset of domain A will be 6 and 8. Okay, just look at the images under those elements in this subset. We get another set, 6, 8, right? So very simple. Okay, I think we can do another example. Okay, so this example is defined from R to R by the rule f of x equal to x plus 1. So that's a linear function. So let's assume the closed interval from 0 to 1 be, all the real numbers from 0 to 1, including 0 and 1. And then the question, what's the image of this subset or R? Okay, so this interval is a subset of R. What's the image of that? Okay. It turns out that's from 1 to 3, because if you plug in 0 for x, you get the 2 times 0, so that's 1. And you plug in 1 for x, you get 2 times 1, which is 2 plus 1 is 3. So that's the closing interval from 1 to 3. Or you can easily, prove this by inequalities, because the interval from 0 to 1, including 0 and 1, is equivalent to the inequality of x greater than or equal to 0 and less than 1. If you multiply 2, each part of this inequality, you get 0, less than or equal to 2x, less than or equal to 2. And if you add 1 at each part of this compounded inequality, we call it, then you get 1 less than or equal to 2x plus 1 less than or equal to 3. So that means the function value f is from 1 to 3 into 1 to 3, right? Okay. So that's just one part of it, and then you can easily check that if the function value f or y is any number between 1 and 3, then y minus 1 will be from 0 to 2, and you divide 2, so that'll be from 0 to 1. You can do 1, 0, and 1, right? You can use the same argument using the same inequalities if you want, the same procedure. Then you can see this, this y minus 1 over 2 is from 0 to 1, or so if you plug in this y minus 1 over 2 as x in the function f, then you get 2 times y minus 1 over 2, which is y minus 1, and then plus 1, so that's equal to y. So that means, each number y in the closed interval from 1 to 3 has a pre-image, which is y minus 1 over 2, from this closed interval from 0 to 1. Okay. So that actually confirms this closed interval 1 to 3 is the image of closed interval from 0 to 1. Okay. So each number between 0 and 1 and 3 has an image between 0 and 1. So that proves the conclusion. Okay. The image of 0, 1 on the F is set 1 to 3. So you have to prove in two ways. Although it's pretty simple in this case and obvious. Well, in the last sentence here says any function f from A to B, we have f of A equal to mf and the image of f. Of course, if you take the subset S to be the domain A itself, then the image of the domain is the image, right, of the function. So the range. That's but this is just a notation. You can write the image of f as f of domain A. Pretty straightforward. And I guess we got a little thing left in this section. We're going to finish next week. Any questions? I think everything so far is pretty easy.
Yes,